Hello everyone. So today we're going to discuss rectangular wave. But before that, I wanted to enlighten you that the picture I used in this slide, in this opening, is a picture gathered from Kaleidoscope. You know, a telescope with a mirror that reflects the light. So, in the same way, rectangular waveguide has those similarity. Okay, so and we will find out why. But the first reason we should ask why we should study rectangular waveguide is why we should study this kind of propagating or transmitting um, electromagnetic waves, especially microwave. Special coaxial cable have been developed that can be used up to approximately 6 GHz. So it should be used for only less than 100 feet. Because if you used it more than 100 feet, it would become lossy. The attenuation constant is high, and it is desirable to just use, especially if you were just connecting two devices. But if you're transmitting a signal that is within 6 gigahertz, coaxial cable is not a desirable medium. It's also expensive, and also due to the technology, in order to be able to use at this frequency, it also become rigid. Another problem is the power handling limit of coaxial cable. So this is problematic. So one solution of this is through waveguides. Most high power microwave energy transmission above about 6 GHz is handled by waveguides. So what is this? So as you can see, this one is a rectangular waveguide, and judging from the picture itself, the material used is a conductor, which most probably a bronze. And in this one, so I'm assuming that perhaps this kind of material is gold. So this is a circular waveguide. Okay, so that's also one of the examples. So as you can see from the picture itself, you can visualize that waveguide is made of conductor such as bronze, gold. Often, insides of the waveguides are plated with silver to reduce resistance, keeping transmission losses to a very low level. So in the latter slide, we will discuss the losses. Okay, and one of the reasons is because of the material used. So in construction of rectangular waveguide, so we use chalk joint. So as you can see, just be familiar of this chalk joint. So as you can see, this one, so it uses interconnect two sections of a waveguide. It consists two flanges connected to the waveguide at the center. This one. So later, also at the latter part of this presentation, especially if you are using waveguide as a transmission, which is a very long system, so eventually you have to use choke joint. Okay, so and also one of the advantage of this is that you can also manufacture it in by pieces, and also this choke joint is used especially if you're having a pressurized waveguide. So you will put a nitrogen gas inside that waveguide in order to avoid moisture content or build-up of moisture. Um, Remember that this moisture is not desirable, since it would add resistance and have an effect on the attenuation of our signal. So this, as you can see in this picture, is a kaleidoscope. So this is an example of kaleidoscope, and if you're familiar of how kaleidoscope working, so it has a mirror that reflects the lights, which makes the picture similar to the picture I've used in the opening part. So I've used this because you can imagine in a way that the signal propagation takes advantage of the wall in the waveguide in order to propagate. Okay, so I've prepared gathered a Matlab's program for this one in order for you to visualize what happened inside the waveguide. Okay, so that's what happened. Okay, so it's just repeating, but you get the gist of it, that since we are dealing with a high frequency, the signal bounces back. However, be sure to understand that it is having a direction, just like presented on this one. So as you can see, there is a direction. So this is a direction, and this is a coaxial cable. Instead, if you are going to insert the signal here, okay, so the electric and magnetic field associated with the signal bounces off inside the walls, back and forth as the signal progresses down the waveguide. So as I have seen in the simulation of Matlab, those are the characteristic of the propagation of electric and magnetic field. Okay. Okay, so the dimension of a waveguide determines its operating frequency range. So as you can see on this one, this is A. So as you can see in this formula, the only responsible for the cutoff frequency is this A. The A is in meter, and the cutoff or CO is in megahertz. So in my next slide, I will give you the basis of this one, but essentially the book simplified it so much that we have this kind of cutoff frequency. Okay, at its cutoff frequency and below, a waveguide will not transmit energy. A waveguide is essentially a high-pass filter. So just to visualize what is the frequency response, that assuming that this is the graph, okay, meaning above the frequency, the energy or the energy will be able to transmit. However, if it's below than that, which is in this part, it will be attenuated, and thus there will be no propagation. Okay? So as the operating frequency decreases, the angle also decreases and the path between the sides shorten, and when the operating frequency reaches the cutoff frequency of the waveguide, The signal simply bounces back and forth between the sidewalls of the waveguide and no energy is propagated. In the preceding slide, there is a comparison between the high frequency, the medium, and also a frequency operating at a cutoff frequency. So, as I said that I'm going to discuss where is the basis of this one. Okay. So the dominant mode in particular waveguide is the mode having the lowest cutoff frequency. For rectangular waveguide, this is TE10, which this 1 correspond to M and 0 correspond to N. And this one can also be rewritten as speed of light divided by 2, and then this one. But this time, I'm going to evaluate using M is equals to 1 and N is equals to 0. Therefore, this one is cancelled, resulting into A. This one should be A. Okay, and then simplifying it, it would become 3 times 10 is to 8 over 2A. That's why this is A. That's why you have this kind of formula. But this one is in Hertz. So that's why it is only 300 because of the unit of megahertz, which is the result of this computation is within in megahertz, while this one is in hertz. So this is simplified because it accounts the lowest possible frequency, which is in TE or transverse electric field, where M is equals 1 and 0. Okay, so the lowest cutoff is called dominant mode in rectangular waveguides. This is TE mode and usually the T of 10. The different modes which have the same cutoff frequency are called degenerate modes, mode in any waveguide. So this is a good to know regarding the modes in waveguide. Okay, so why it is a high pass filter? As I've said a while ago, there will be a comparison between the frequencies. As you can see, this one is high frequency, the letter A. D is a medium frequency, and so on and so forth. Okay, so imagining this is within the top view. So the signal propagates and then it bounces back. Same concept that happened, almost the same concept that happened in Kaleidoscope. So as you can see, in high frequency, it has this angle of incidence. Observe the angle of incidence as we go nearer to the cutoff frequency. Okay, so as you can see, the angle of incidence decreases as stated here. When the operating frequency reaches the cutoff frequency, the signal simply bounces back and forth the sidewalls of the waveguide and no energy is propagated, as illustrated here in the letter D. So the angle of incidence decreases. So as you can see, it decreases from here to there and looks like a compression, and eventually it becomes this one. So that's why it is a high pass filter. Okay, so it is important that we should consider this transverse electric field and transverse magnetic field. Since we are dealing with electromagnetic waves, it is reasonable that there is an electric field and there is a magnetic field. So pay attention to this one. Okay, this is E, and in magnetic field this is H. So as you can see, it is inverted in 90 degrees, which is I put it here as a review that this is the electric field and magnetic field. As you can see, it is in 90 degrees. So that's why when analyzing this waveguide, it is usually examined between the electric field and the magnetic field. A vertical probe is generating vertically polarized wave with electric field and a magnetic field at a right angle to the electric field. The electric field is at right angle to the direction of the wave, so it is called a transverse electric field, okay, also called TE. So that's why on the previous slide you have encountered this one, okay, which is the dominant mode, which is the basis of the cutoff frequency of the book. In the figure B, which is this one, shows how loop would set up the signal. In this case, the magnetic field is transverse to the direction of propagation, so it is called transverse magnetic field. So in this one, attenuation and losses in rectangular waveguides. So losses in dielectric, the medium in waveguide is normally a low loss dielectric such as air. So that's why in our previous slide we have this choke joint in which some long waveguides are pressurized with nitrogen gas to reduce moisture buildups. So one of the reasons of that is to reduce the attenuation and losses in rectangular waveguides. So wall losses, or the number 2 factor, is the resistance of the wall is the surface resistance. So this is the resistance that is affecting the propagation of the electromagnetic wave. So this is the attenuation. So this is from dielectric, and this is the wall losses. That's why I iterated in the previous slide that they uses silver so that to reduce the losses and attenuation. So thank you for listening.